is, so we were discussing the point number 3 of tangent length BT1 or BT2, and it's equal to R tan phi by 2. So if you look at this triangle, BT1O or BT2O, so this angle over here at T1 is a right angle triangle, and let me annotate for this. Yeah. So over here you have angle phi by 2, and if you apply the trigonometric relation with 90 degrees at T1, so you get the length BT1 is equal to R, which is the base, tangent phi by 2. And similarly, BT2 would have the same relation. So then we have the length of the curve, which is the length of the arc T1 ET2, and this is equal to pi R phi over 180 in meters. So what we are talking about is the length of the curve, which is T1 E T2, this total length. So if you remember the equation, so if you have an arc over here, you have an angle, and this length and the radius. So this length is equal to R theta. So the same relation, if you apply over here, the curve length T1 T2 is equal to the radius times the central angle, which in our case is phi by 2 plus phi by 2. So that becomes phi. And then you convert it into radians. So that is how you get this value over here, which is pi R phi over 180. So this is how you calculate length of the curve. And then you can do it if it's given in degrees, but we would be working in radius. Then we have length of the long chord. So this is the length of the long chord. So if you remember, the long chord is the distance T1 D T2. And in order to find that, the total length, which would be smaller than the curve length of T1 E T2. So in order to calculate that, we would take the triangle T1D O or T2DO, and we have a right angle at the point D, and the angle at point O is pi by 2. And then again, by using the trigonometric relation, we can find out the distance T1D or T2D equal to R sine phi by 2. And since it is half the distance, you multiply it by 2, so that the total distance becomes 2R sine phi by 2. Then we have the apex distance, which is BE. So this distance from the point B to the point E. Now, we're calculating this, and you can derive this, and the relation comes out to be R secant phi by 2 minus R, taking our common R into secant phi by 2 minus 1. And then we have Word's sine of curve, which is this distance DE. So you can basically calculate this distance by um, taking the distance OE, which is the radius, right? Because we're talking about a simple circular curve, so distance OE is the radius. And from that, you can subtract the distance OD, which can be calculated from the same triangle ODT1. So that comes out to be R minus R cos phi by 2 or R into 1 minus cos phi by 2. Now, these distances, apex distance, which is a distance BE, and the worst sine of curve, which is a distance DE, they can be very useful in finding out if the work that you have done in the field is correct. So once you're done laying out the curve in the field, this can serve as a check. You can quickly just calculate the distance BE, and then you can compare it with the theoretical value, or you can calculate the distance DE and again compare it with a theoretical value, and you can know if the work that you have done is correct. So these are some equations that we would be using in designing the curve. Then we have these three definitions: full chord, initial subchord, and final subchord. So I'll get to that when we solve the numerical. So now in the book, they have given different methods by which we can actually set out the curve or lay out the curve in the field. Um, so we won't be going into all of them. I'll just give a brief idea of how the first method works, offsets or ordinates from the long chord. So basically in this method, what you do is that you locate the point T1 in the field, and then you draw a straight line to the point T2. And then theoretically, you find out that from this line, from this long chord, what are the ordinates of the curve? So essentially what we do is we find out these distances. So at regular interval, you take the T1, x is equal to 0, and at T2, x would be equal to the length of the long chord, and then you choose an interval, x is equal to 5 or x is equal to 10, depending on how much you want. And then at each distance on the long chord, you calculate the distance from that point to the curve. So that is called as the offset to the curve. And obviously the maximum offset that you will have would be at a distance x is equal to the length of the long chord divided by 2. At the point D, you would have the maximum value. So this is how this works. So they have given an equation as well. So this equation, so which says that in order to find out the ordinate at any distance x, you can use this equation. So ordinate at any distance x is equal to r square minus x square, which is a distance along the axis, minus r minus o naught, and o naught is the maximum ordinate, which is the worst sine of curve. You can calculate it from the equation that we have. So this is a very basic method of doing it. Other methods, we won't go into them because they're not included. We will switch to the method that we will be using in the lab, which you will actually use to lay out the curve in the field, which is the last one. So let's just quickly go on to that. So which is this one? The horizontal curve setting by deflection angle method or Rankines method. So very briefly, in this method, what we do is that when you are in the field, you locate the point T1, and over here you'll have the point A, and you draw a straight line, which would be B over here, but you extend it further. So this the tangent you draw, and then you set up your instrument at the point T1. So you would have your theodolite at the point T1, and you locate the point T2. Afterwards, using this method, we calculate the deflection angles from the tangent. So from the tangent T1B, we calculate the deflection angles. So at some distance, we can calculate what is the angle of the curve. So you would set up your instrument equal to 0 degrees on this line, T1B, and then whatever the value is, you locate the point. So as you go further, the value would keep on increasing for the curve up till when you reach the last point. So let's say your last point is T2, and you find out this deflection angle. So how much would this angle be? So if you remember the diagram for a simple circular curve, this would be equal to 5 by 2. That means your last deflection angle would be equal to 5 by 2 when you lay out the curve. So basically what we're doing is that we are finding out deflection angles from the same tangent to different points on the curve. And that is how we locate. So in order to locate that point, we need one, the deflection angle, and two, we need to again know at what distances we are finding out the angles. So you can have infinite value of the angles. So for that, what we do is that we take this line again. So point A, point T1, over here point T2, and over here you have B. So then we take chord lengths. So if this is going to be the curve, and let's say the curve length is 30 meters, let's say. So we can take the chord length is equal to 5. So at every 5 meters along the curve, we are going to find out the deflection angle values. So you can use your measuring tape from the point T1, open it 5 meters, and then take the angle. And when the two intersect, you can set out that point. Similarly, from this point to this point, it would be 5 meters, the value of the deflection angle, which we calculate theoretically, and you set out these points. So in this way, we can set out the entire curve. So in this diagram, you can see as well that what they have done is that they are giving you the deflection angle values, these values from the tangent at different points. And when you sum them up, so that the last deflection angle that you would get, that last deflection angle should be equal to 5 by 2. Now in this method, or the equation that we are going to use, so let's quickly see the equation before we discuss this further. So the equation for finding out the deflection angles is this one. So this is equal to 1718.9 multiplied by ln, which is the chord length, divided by the radius of the curve. And remember, this equation gives you the deflection angle in minutes. So you need to convert into degrees or whatever notation you want to use. But this is the equation essentially that we are going to use. And if you see this equation, 1718.9 is constant. R is a radius, which is again going to remain constant for different deflection angles. And the only thing that is changing is ln. Now, if you are using the same chord length for all the points, then that value, even that value would remain constant. So the deflection angle would essentially remain constant. And how does this work? So if you see this figure over here, for the first point over here, they calculate the angle, which is this one. Now, if we draw this, so essentially what we are doing is we are selecting a point over here, and this is the deflection angle. Now, for the next point, let's say the point is here, the deflection angle is from the previous point to the next point. Similarly, for the next line, the deflection angle is from the previous point to the next point. So that is why this deflection angle value remains constant. It was 1718 multiplied by ln divided by r. So since this is from the previous chord or from the previous line, this value remains constant. And for the last value to become 5 by 2, what you have to do is you have to take the summation of all the deflection angles so that they add up, and then you get the last value is equal to 5 by 2. Now in the field, there are different methods by which you can do the same thing. One way is that you set up your theodolite value equal to 0 after setting out each angle, or you can work out by adding them up that what the next value is going to be from the initial tangent. So you find out each value from the initial tangent by adding them up, and that makes it easier for you to set it up. So let's see this in the form of a numerical, which would make it easier for you to understand. So let's see this question. Two tangents intersect at a chainage of 1250 meters. And before I proceed further, I hope you remember what chainage is. So chainage is basically any distance from a reference point. So it's a linear distance. So in our case, what they're saying is that two tangents intersect. And what tangents are they talking about? They're talking about the tangent BT1 and the tangent BT2. So this is what they're talking about. So they're intersecting at the point B, and the chainage of B is 1250 meters. Now, usually in construction projects, we work with chain edge, usually we don't. But since in the question they have given us chain edge, so we'll just work with that. The angle of intersection is 150 degrees. Now see, they haven't given you angle of deflection. They have given you angle of intersection, which is this one. So this angle is 150. That means the angle of deflection would be equal to 180 minus 150. So angle of deflection is 30 degrees. Calculate all data necessary for setting out a curve of 250-meter radius. Now they've also given you the radius, which is 250, by the deflection angle method. The peg interval may be taken as 20 meters. So they have given you essentially ln themselves, which is 20 meters. Now, like I told you before, for any design or layout of a simple circular curve, they would give you either the intersection angle or the deflection angle, which they have, and they would give you radius or degree of the curve, which they have given you the radius. One additional information that they have given you is the chainage of the point B. Now, that can be or cannot be used, that depends, but since they have given you it, so we are going to use it in the question. Now, this is the data that we have. So the first thing that we should do now is to find out the chainage of the point T1, because that is basically essentially the starting point of the curve. Now, how we can do that? They have given you chainage of the point B, which is 1250 meters. That means that there's some point over here. Let's call that point X. From the point X, the distance, linear distance to the point B is 1250. Now, from that point X, the distance of B is 1250. Now, we want to find out from the point X, what is the distance to the point T1. So if we subtract from this distance BT1, which is the tangent length, we can find out chainage of the point T1. Now, if you remember the equation for finding out the tangent length, it was R tan phi by 2. So the radius is 250 and angle of deflection phi was 30. So phi by 2 becomes 15. So the tangent length becomes 67.5. Now, if you subtract it from 1250, you get chainage of the first TP, tangent point. So T1, the chainage of T1 becomes 1250 minus 67. So it becomes 1183. Now we can calculate the length of the curve. So T1, T2, the length of the curve. And if you remember, it comes from the simple equation L is equal to R theta. So the length of curve becomes R into the deflection angle, but then you convert into radians, multiply it by pi by 180. So over here you can see the equation and you get the length of the curve as 130.89. Now the chainage of the first point T1 becomes 1183 and the chainage of the second point becomes 1183 plus the curve length. So it becomes 13 yeah, it becomes 1313.89 meters. So now we have chainage of the point T1 and we have chainage of the point T2. Now we'll talk about a concept which I skipped before, which was initial subchord, final subchord, and the full chord. Now the concept is really simple. And this concept is only applied when you're working with tangent. Otherwise, you don't have to apply this. So let's say that the total length of the curve is 130.89. So from the point T1 to the point T2, this distance is 130.89. Now remember that in the equation that we use for finding out the deflection angles, you need to find out the deflection angles for different points on the curve. So that means you need to cover the full length of the curve in order to find out the entire sketch of deflection angles. And we cover that length on the curve by using these chords. So if you join the 2 points with these chords, that means that the length on the curve is approximately equal to the length of these chords. Now, as the curve length is 130.89, that means we need to cover 130.89. And they had given us the chord length equal to 20 meters. So the interval was 20. Now, if the interval is 20, that means we can have 6 chords of 20, which would make 120 meters. But then we would be left with 10.89 as the length of the last chord. So what I would do is I would call my normal chords as full chords, and this distance which is left at the end, I would call it as final subchord, right? Another way is I can use this distance in the beginning and I can call it as initial subchord, and then afterwards I can use the full chords. But in this question, what they have done is that they are dealing with chainage. So the chainage of the point T1 is given as 1183. Now, what they would do is that they would take the first chord in such a way that we get a number with a 0 at the end. So 1183, and I want to make this the distance of the first chord as 1190. So that means I would add 7. So that means 7 becomes the length of my initial subchord. Afterwards, I use the chord length which is given 20. So 1190 plus 6 into 20, I get 1310. So this is the distance that I have covered on the curve, and the last point is supposed to be 1313.89. So if you subtract 1313.89 from this value, you subtract 1310, you get 3.89. So that means now I have my initial subchord of 7, 6 full chords of 20, and the final subchord of 3.89 meters, right? So this gets a bit confusing when you're working with these chainages, but this is in your control. You can deal with it in any way that you want. For example, another way would have been I don't convert 1183 to 1190. I don't have to do that. See, so I can use this method that we discussed before. Use 20 meters chord length, and at the end, use a chord length of 10.89. So that depends on you. You don't have to follow this convention. But since the book has done it in this way, so I had to explain it. But if I were you, I would do this with the other way. Don't go into changes. Just use assume that T1 is at 0, and then use chord lengths of 20 until you reach the last point for which you will have to use a different chord length. So that is it. So now once we have that, we can apply the equation for deflection angles. Now, since the book has done it in such a way that it has initial subchord, full chord, and the final subchord, so for the same equation, the radius remains the same for all three. The constant 1718.9 is there. And then you replace the values of ln, which is initial subchord, full chord, and the final subchord. So 7, 20, and 3.89. And then you get three values of deflection angles. And then you can apply the check as well to see if your calculations are right. The summation of all the angles, the deflection angle for the initial subchord, deflection angle for the final subchord, and remember that for the full chord, we're using it 6 times. So you have to multiply it by 6. So if you add these, you should get the deflection angle 5 by 2. which we have seen a lot of times in the previous figures. So if you get that, that means your calculations are right. And then you can use calculate the apex distance and the worst sign of curve. And like I discussed, that these are very useful when you're doing it, laying out the curve in the field. Now the important part of how to set up this table. So if you see this table, we are starting with the point T1, which is the initial point of the curve, or where the curve starts. You have T1. And after that, you have a number of points. And the total number of points up till the point T2, which is the end point of the curve. So these numbers depend on the interval that you're using, or the length of the full chord that you're using. So we were using 20 meters. So based on that, we had P1 at the point of initial subchord. Then after 20 meters each, we had a number of points. And at the end, we had the final subchord. So if you use 10 meters instead of 20, so these points would increase. Then they've written the chainage. So we had 1183, and we added 7 in that. And after that, you can see there's interval of 20. But for the last point, the interval is smaller. So the chord length was 7 in the beginning, then it was 20, and then it was 3.89. So based on this, the deflection angle would be, we would get three values, one for the initial subchord, one for the final subchord, and then the same value for all the other ones, because the chord length remains the same. And then for the total deflection angle, you can just keep adding them. So 0 degrees 48 minutes and 8 seconds plus 2 degrees 17 minutes 31. So you will get this value, then add these two and you would get these values. You can keep adding them up. And then angle to be set on the theodolite, that depends on your least count. So if the least count is 5 seconds or 10 seconds, depending on that, you can round them off to the nearest value and set it up on your theodolite. So this is basically how you design the curve. By that we mean to find out different aspects of the curve, and then this table helps you in setting out the curve in the field.